The method that I would like to describe today is a numerical procedure that enables us to calculate resonances by using a variational principle that will be studied later. So let me write a numerical method for calculating resonances based on complex variational principle proved in chapter 7. So we'll study it later. Okay, let's describe what we want to do. As for a simple case, we'll start with one-dimensional, although that what I'm going to describe can be done for a multi-dimensional and multi-particle systems. So let's assume that we have this Schroeder equation that we want to solve. And let's put here discretization conditions. And if we take x to be x ei theta, as I described in my first talk, and we will discuss it much more after you will read the chapter, I think it will be chapter 5 in the book, when we speaks about complex scaling and the different methods that make the resonance wave function to be square integrable. Then in such a case, the v of x, which is the potential in this case, is come to be vx ei theta. And this can be done only for analytical function. And this is very important property that I will use today in order to calculate the variationally using numerical method, the energies and the wave functions. So let me say one sentence without any proof. What is the variational principle that we are using? And C stands for complex. So this is for complex. So we assume that even if the wave function that we have here is obtained as eigenfunction of non-Hermitian operators Hamiltonian due to this scaling of the coordinates, we can expand psi n as linear combination of basis function. And in the case of complex scaling, these coefficients will depend on theta. But I omit the index theta to make it more general. And what are these phi j? Just as an example, I can take it to be as equal to 2 over L sine j pi x plus box divided by 2 divided by L. And box is the size of the box that we are using, that x is varied from minus box to plus box. But this is only an example. It doesn't have to be so. And then if we do this, we end up with a matrix representation of the operator when these coefficients here come to be this, and we put it approximately like this because when we make this expansion, we need to use infinite number of basis functions, but now we take only n, and so this matrix is n by n. And the Hamiltonian matrix elements are, of course, that we are using, we can say the Hermitian matrix elements is J prime J. If you use such a basis set for which the kinetic energy operators is diagonal, they represent by diagonal terms, we'll have here, in this case, for example, let's put it this case, is h bar squared divided by mu. It's the reduced mass of the problem, J pi over L, which is this, actually, here L is our box. So I could put here L over the 2, but never, it doesn't matter. And here's delta J prime J plus phi J prime V of X phi J. So the problem that I would like to discuss is related to the way how one can calculate these potential matrix elements, even in cases that it's very hard, or sometimes it's almost impossible, or maybe impossible, to calculate in an analytical way these matrix elements. So this is what I would like to discuss now. How to calculate these matrix elements. Okay. So let me start by saying that phi J prime V phi J, let's put it to be like this. This is my claim. It's equal or about equal to summation over L from 1 to m, which is greater or equal to n. This is the size of our Hamiltonian matrix, how many basis functions we are using to construct the Hamiltonian, which is equal to T J prime L, T J L, complex conjugate, in the case that the basis functions are complex, not like in sine functions. And then V is equal to, we put here as a function, is lambda L, where these coefficients are eigenvectors and eigenvalues of the following matrix. So we construct a matrix, call it X J prime J, which is phi J prime X phi J. And when we diagonalize this matrix, we get T vector L equal to lambda L TL. And since we use orthonormal basis set, and we use here the scalar product as usual, this X is Hermitian matrix. If it's real, it's real symmetric. If it's complex, it implies that X is equal to X transpose complex conjugate as usual. And these eigenvalues have to be real. So this is what we say. And the question is why? And this is what I want to prove now. So the proof is based on the following argument. That first of all, we can see that this eigenvalue problem, we can write it to be like this. That lambda is a diagonal matrix where these eigenvalues are on the diagonal. So this is quite clear. This is lambda diag is a matrix, lambda 1, lambda 2, blah, 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 zeros. And here the last one is lambda m. So this matrix is m by m, as I stated here. Now, if we do this, it's clear that X can be reconstructed from the eigenvector matrix and the eigenvalue and the eigenvalues, and it's equal to T lambda diagonal, I'm sorry, T transpose complex conjugate. So this is an important simple property that we are using. And let us continue and show why we say it. In order to understand and to prove it, let's take the potential and use the argument that I said at the beginning that is an analytical function of x. Therefore, we always can expand it in Taylor series expansion and call it here m, for example. And it always converges from any x. Taylor series expansion for analytical functions, the radius of convergence is infinity. You can put any values of x and it will be converged. Now it's easy to see that phi j prime v phi j come to be summation over m, when here we have phi j prime x to the power of m phi j. Let's see what is happening when m equal to 1. For m equal to 1, it's phi j prime x phi j, which is x j prime j that we wrote here. For m equal to 2, we have phi j prime x square phi j, and we can write it to be a summation from like this, from L1 to 1 to infinity to phi j prime x phi L x phi j, when we use the fact that this is the unit operator is this. This is what we use. Now, in the numerics, we don't take to infinity, and therefore we assume that if we take here m to be large enough, then this will be equal, about equal to unity. This is our approximation. So this is very important point in our derivation. And when we do this, and we take here equal to m, and then we put here equal to this, one can see immediately that what we wrote here is here, this is x j prime l, and this is xl j. And therefore, what we have here is the matrix x to the power of 2. And we take here the matrix element j prime j. So this approximation enables us to estimate this power by taking the matrix x to the square. Now, what is interesting here, of course, that if we take now what we wrote before here, we can say that x, the matrix square, is equal to, or maybe, yes, to t lambda diagonal square t transpose complex conjugate. This is what we say. Why I say it? It's very easy to see it here. Let's multiply here x matrix and x matrix. Then this is x squared t. This is exactly what we want to show it here. Then if you take xt we know what it is. It's equal to t lambda diagonal. And then what we prove here, that x squared t is equal to t lambda diagonal square. And this is, of course, correct. because the eigenvectors of x squared are exactly like the eigenvectors of x, and the eigenvalues are only come to be to the power of 2. And from here to here, it's clear. We multiply from the left by T transpose complex conjugate, and then we get this equation. Now, it's very easy to see that using this approximation, that we can generalize it to be like this. So, using this, we can see that if we are coming back to this equation, we have here summation over m from 1 to infinity, am, and here we have the matrix x to the power of m, and then to take the matrix elements j prime j. But this is what? Is summation over m from 1 to infinity, am, and then we have what I wrote here is t lambda diagonal to the power of n times t transpose complex conjugate, and then we need to take, of course, j prime j. Let us continue here. When we continue here, we say phi j prime v phi j, this matrix element, is summation over m equal to 1 to infinity, and then am, and this is summation over L from 1 to m. This is our approximation, so let's put it like this, approximation. It's t j prime L. T, we need to take the transpose, so it comes to be tjl complex conjugate. And here, it's lambda L to the power of n. This is what we got. Then we can write this is equal to L equal to 1 to m, of t j prime L tjl complex conjugate. And here I change the order of the summation is m from 1 to infinity, am lambda L to the power of m. Well, this is exactly the Taylor series expansion of the potential as we stated before. As you can see it here. You see, this is exactly what we wrote before. So let's return to the expansion here. This is equal to v of x, and therefore we have summation L equal to 1 of m t j prime L tjl complex conjugate. I'm sorry, this is here lambda L, and v x equal to lambda L. I repeat, this is expansion of the potential when we substitute instead of the variable x, the number lambda L. So this is what we got in the end, and therefore this is phi j prime v of phi j is about equal to this. We can write it in a different way, that the matrix V that we are interested, the potential matrix element, or the potential represented in basis functions, when this is n by n, is a product of T, which is a matrix n by m, you see by these indexes, times V diagonal, which is a matrix M by M, time T transpose complex conjugate, the dimension is M by N. So this is the trick. We numerically calculated the potential matrix elements using the assumption that our basis set is large enough to describe the unit operator. And actually, we don't need to describe it to be the unit operator in all space. It needs to be in the space, in the subspace, where the potential get non-zero values. So this is a key point. We speak about potentials that are vanished somewhere in one dimension. If you go to x infinity, they go to 0. And if it's the x is vary from minus infinity to infinity, also in minus infinity, we want that it will be go to 0 or to get to a high value. So we need that to have actually here thresholds in this problem and this potential. So we can expand it in Taylor series expansion in a simple way. And the region when the potential is dominated by exactly the region when we want to have the unit operator of our basis functions. Even to be more accurate, not the potential should be described well, but the eigenfunction. So if we have a potential where the wave function is localized in space in a given region, the unit operator should be able to be describe well this function. So this is more accurate to say it. So let me continue and get to a nice result that is known as DVR, discrete variable representation from here. So our Hamiltonian matrix, in our case, is the kinetic matrix, which is diagonal in our case, because this is how we choose as a basis set, plus V, the potential, which is T, V diagonal, diag, T transpose T complex conjugate. Now, it's easy to see that we can define, I should put it here, a new matrix, which is T transpose complex conjugate H T, which result in T transpose complex conjugate K diagonal T plus V diagonal, when this V diagonal is V lambda 1, V lambda 2, blah, 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 and zeros. And this is the very interesting result, since now we can construct this non-diagonal matrix for the kinetic that represents the kinetic operator once we decide about our basis functions. So we did it only once. And then when you write a code to diagonalize this matrix, in one line, we can say what are these potential matrix elements. Since it's diagonalized matrix, when on the diagonal, you have the values of the potential in different grid points that were calculated by diagonalization of the matrix X. So it's easy to use the same code for large varieties of potentials. The only thing that you need is to change in one line the potential function, the function of the potential. Instead of writing one function, write another function. Provided, and this is very important to remember, that your potential is analytical function of X. Why it's important? Because our proof is based on this assumption that the potential is analytical function of the variable, and therefore we can use Taylor series expansion as I described here. So this method is very powerful and can be used to calculate resonances. And maybe in the end, I will describe to you what different systems you can study this way. So let me go to the beginning and to describe so the first example that you can study is what I mentioned in the shape-type resonances. When you have a molecule, the atomic molecule interacting with when interacting with a field that make it to be rotationally excited. So bottom line, you have Hamiltonian, where the molecule is rotating to a given J state, and now you want to calculate the bound states and the resonances by using complex scaling. Another case, which is one dimension, but it's described the phenomena, we can think about a potential V of x that we want it to be whatever, but analytical function, and then therefore lot describe something like this. And I assume here that everything is an analytical one, general. And here we have threshold energy, and here we have threshold energy, which is exactly the same. And if you'll do what I said, and you'll scale the coordinates by exponent, if you take x to be xe, if you take x to be xei theta, if you do this, then the spectrum that you will find in this numerical calculation is the following. You will see that if this is the real part of the eigenvalues that you will get, and this is the imaginary part of the eigenvalues that you get, and that they will be discrete in your case, you will see in your case the bound states. And in what you do here, you'll see that the continuum is rotating by the angle 2 theta. However, if now you will change the potential to have also barriers. So, sorry, we have this potential. And now the resonances will decay from here outside, and decay from here outside. And from here they can decay also to this direction. And from here they can decay also not only to the right, you can decay also to the left. So you have resonances here and here that can decay to both directions. And then you will get complex eigenvalues that are theta independent, that are resonances. So let me repeat on what I say here. If you have a potential that is an analytical function that has one threshold and have a barrier here and barrier here and a barrier here, very general, can be more barriers, and this potential has potential wells below the threshold, then we have bound states and resonances, and the resonances are localized in this well here and the well here. This resonance is located here and here. Decay to here, decay to here, decay to here, decay to here. And what you end up is such a spectrum. Bound state, and the resonance is here. Now, let's assume that we have with this we'll finish. Let's assume that our potential looks very similar, but has different thresholds. So the potential is look so what is the difference between what you have done before and now? Before, you have one threshold. So E threshold number 1. And here we have E threshold number 2. Now, here in this picture that I put here, I put only 2 barriers, not 3 as before. We have here bound states. They are localized in this region. And we have resonances that are localized here. Call it resonance type 1. And we have also resonances type 2. What is the difference? These resonances can decay only to the right because they are above the threshold energy here. This resonance can be decayed to here through the barrier or above the barrier to the left, but also to the right. When it's come to here, the particles are coming with this kinetic energy. When the particles decay to the right, they decay with this kinetic energy, with larger. They move faster. So they are moving to this direction fast and more slowly to the other direction. How you can see it in your calculations? In your calculations, when you plot the real eigenvalues as function of the imaginary eigenvalues, or the imaginary as function of the real one, you'll see the bound states. You'll see the 2 rotating continuum. This will be the E threshold 1, and this will be E threshold 2. You'll get resonances here and resonances here. These resonances are type 1. Resonance type 1. And these are type 2. And the reason is clear, because here this decay to here, to this threshold, and this can be decay either to this threshold or to this threshold. So it's 2 threshold phenomena. So this is a case to show you that you can have different open channels to decay, even in one dimension, provided the threshold energies are not the same. So I hope that this will be useful when you will try to calculate resonances by yourself and see the spectrum and see the wave functions and how the rotational angle of the coordinates make them to be square integrable.